Hello, everyone, and welcome to my talk, The Semaphore Architecture in a Nutshell. My name is Radosław Woźniak, and I'm one of the engineers working at the Semaphore. I'm eager to explore the technical foundation of the Semaphore with you, how it operates behind the scene, how the components interconnect, and what happens from the moment of you push the code until the build is finished. The Semaphore is an efficient CI/CD platform, yet its simple appearance masks the complex architecture consisting of over 30 microservices, various communication protocols, and a strong infrastructure that ensures smooth pipeline operations. We will break down this into the key sections, focusing on both how the semaphores run under the hood and how developers interact with it. To give you a roadmap, let's take a look at the agenda. We will begin with the overview of the semaphore architecture, what technologies we use, and how they are fit together. Then we will move into the CI/CD processing, this core flow where semaphore takes a git push and turns it into the running job. We will break this down into key components, how webhooks triggers pipeline, how jobs are orchestrated, and how results are communicated back to the users. After that, we will cover the CI/CD management, where users interact with Semaphore to configure the environments, manage projects, and control the access. Here we'll discuss how communication between services is structured, how authentication and authorization work, and how we introduce new services into the system. Now that we have a clear structure of the talk, let's start with the foundation, the semaphore architecture. The understanding this will give us the context that we need before diving into how the system operates. Semaphore is a powerful CI/CD platform designed to be both scalable and easy to use. While it may seem simple from the outside, under the hood it operates on a sophisticated distributed architecture, and every part of the system is designed for high performance, fault tolerance, and seamless automation, ensuring that developers can focus on shipping the code while Semaphore takes care of the heavy lifting. But what makes this possible? The key lies in Semaphore's core technologies, the way service communicates, and platform and infrastructure that ties everything together. Let's take a closer look. At the heart of the Semaphore architecture, there are core technologies that powers its reliability, scalability, and efficiency. Elixir is the foundation of our system, chosen for its fault tolerance, concurrency, and ability to handle high load environments. All that is essential for CI/CD platform that processes thousands of jobs. While Elixir is a primary language, we also use Go in certain areas where it makes sense for performance and efficiency. There is also a legacy service in Ruby, but that is in the process of being rewritten in the Elixir to align with the rest of the stack. And of course, we have some HTML and JavaScript for presentation layer. Beyond the technologies themselves, communication between the services is a key to make everything run smoothly. External communication happens over the HTTP, which is how users interact with Semaphore API and UI. But internally, we rely on the gRPC, which gives us better performance and strict contract between the services. For asynchronous messages, we use Rabbit, which allows our services to handle background tasks efficiently and scales as needed without blocking the execution. All of this is built on a robust platform designed for scalability and resilience, and the Kubernetes is there in the core, ensuring that our system can scale dynamically based on the workload demands. For storage, we use Postgres as our primary database, while Redis helps speed up operations with efficient caching. And of course, as I mentioned before, the RabbitMQ plays a key role here as well, acting as the backbone for asynchronous communication. These strong architectural foundations allow the Semaphore to handle workloads efficiently. So now let's see how it comes all together. Semaphore is designed to support two primary workflows. Each plays a crucial role in how the system operates. The first is the CI/CD processing, and this is the backbone of the Semaphore. It is a main execution flow where jobs are triggered, orchestrated, and then executed, ensuring that every code change is built, tested, and deployed seamlessly. From the moment a Git push is detected, Semaphore takes over processing the event, defining the pipeline, preparing the jobs, and finally executing them on the agents. And the best way to understand the processing is to follow the code change from push to execution. And at the heart of this process are three key components that handle the events, orchestration, pipelines, and executing jobs. As you can see here, it all starts with the hooks processor, which acts as the system first checkpoint. Its job is to detect incoming events from the Git repository, validates them, and ensure they are correctly formatted and authorized before passing it further to the system. Once an event is approved, it moves to the next stage, to the pipeline processing. And here, Semaphore reads the YAML configuration, determines the sequence of execution, and orchestrates dependencies between different pipeline stages. And finally, when everything is defined, the process moves to the job processing. And this is where the system gathers all the necessary resources, assigns jobs to the available agents, and ensures smooth execution. These components work together in a structured sequence, as you can see, ensuring that every code change flows seamlessly from detection to execution. Let's go now deeper and see how it works step by step. The first step in this CI/CD execution is a hook processing, where Semaphore listens for incoming events and decides whether they should trigger a pipeline or not. And this step is crucial. It ensures that only authorized and correctly formatted webhooks moves forward, preventing unnecessary or unauthorized executions. To handle this, Semaphore relies on two dedicated services. The first one is Hook Receiver, which accepts incoming webhooks from the Git repository. Its job is to verify whatever the event is something Semaphore should process and checks its authenticity. Depending on the repository provider, it validates it through the signature of the payload, or it's checking the secret key from the headers. If everything checks out, the event is accepted and passed forward. And this is where the hook processor takes over. And this service parses the payload, converts it to our internal format. It also enriches the data with additional details from the organization and projects and other internal APIs, ensuring that all necessary context is available before moving forward. The processor hook is then stored in the database for traceability and make it easy to debug and audit later if needed. With the webhook validated and processed, Semaphore moves on the next stage, the pipeline processing, and this is where the system interprets the pipeline definition and orchestrates the execution. And here, with webhook successfully processed, Semaphore now knows that the pipeline needs to be executed. But before the job can run, the job needs to be structured correctly. Dependencies must be managed. The execution must follow the intended sequence, and this is where the pipeline processing comes into the play. At the heart of this stage, there is a service called Plumber, which responsibility is to define and orchestrate all the pipelines. And Plumber doesn't execute the job itself. It focuses on interpreting the YAML configuration file from the repository, figure out what steps needs to be performed, and ensuring that everything happens in the correct order. If pipeline has multiple stages with dependencies, Plumber ensures that they run in the right sequence, preventing jobs from executing too early or out of the sync. Once the pipeline structure is finalized, plumber coordinates execution, passing the job definition along to the next stage in the system. Think of a plumber as a conductor of the orchestra. It doesn't play the instrument itself, but it makes sure every section comes in at the right time. Once everything is prepared, it hangs off the execution to the next system in the pipeline. And for those who are interested how plumbers work under the hood, there will be a deep dive talk by Damian, where he will go into more details about how it drives Semaphore CI/CD process. The pipeline is now fully defined, but it's still just a plan. The next step is turning this job definition into the real execution, and this is where the jobs processing comes in. The service responsible for this part is called Zebra, and it plays a crucial role in making sure that jobs run smoothly and efficiently. Before sending the job to the agent, Zebra, also using the internal APIs, collect all necessary details. It fetches secrets, pull credentials for the artifacts, and gather other repository informations. And these steps ensures that when the job starts, it has everything it needs to succeed. Once all the required data are in place, Zebra assigns the job to available agents. From this point, the agent takes over and runs the workload. But Zebra doesn't just hand it off and forgets about the job. It actively tracks the state and moves through different stages. This ensures that jobs are efficiently dispatched and executed in the right order. When the job completes, Zebra updates its final state. But if something goes wrong, like a job exceeds its allowed execution time, Zebra forcefully terminates it and marks it as times outs to prevent it from blocking other jobs in the queue. This structured approach allows Semaphore to reliably track job execution, making it easier to debug issues, retry jobs when necessary, and maintain the clear execution history. Now, while the Zebra is responsible from preparing and tracking jobs, the actual execution happens on the agents. And if you are curious about how agents work under the hood, Lucas will cover this in one of the next talks. And yeah, now that all jobs have been executed and the pipelines are reached its final states, there is one last crucial step, and this is like notifying external systems about the outcomes. And this ensures that users stay informed and the version control system accurately reflects the latest build status. As soon as pipeline completes, whatever its success file or is like cancelled, the system generates the completion event, and Plumber publish this event as a rabbit message, allowing other services to pick it up and process notifications accordingly. One of the key services responsible for notifications is the notification service, of course. Depending on how the system is configured, it can send real-time updates to the Slack or to the webhooks. Another important piece of external communication is updating the status of the commits in version control system. And this is handled by another service called GitHub Notifier, and which this service ensures that repositories receive the latest build results. And this completes the standard pipeline lifecycle, but not every execution starts with a new Git commit. Let's take a look at the other ways pipelines can be triggered in Semaphore. So beside commits, user can also start a workflow by a rerun, or can start only a debug job without starting the whole workflow. Each of these enters the system in a slightly different point, but all of those communications go through the API layer. So when the workflow is rerun, the process doesn't start from scratch from processor. Instead, it begins directly in the Plumber, in the pipeline processing system, And this means that pipeline configuration is reloaded, the jobs are redefined, and execution flows the same structured flow as for new commits. Once completed, notifications are sent just like in the standard pipeline run. On the other hand, when a user starts a debug job, they are not triggering any pipelines, just a specific job. So because of this, the processing bypass the hook processor and pipeline processor altogether and start directly in the Zebra, the job processing system. Zebra gathers the necessary information, prepares the job, and dispatch it on the agent, ensuring that it runs in isolated environment. This flexibility allows Semaphore to handle various use cases efficiently, whatever a developer wants to rerun an entire pipeline or just investigate a single job. Okay, so we explored the entire CI/CD process flow from the moment of commit is pushed to when the job is executed and results are reported to various systems. While it may seem simple on the surface, under the hood, multiple services work together to ensure that every step from detecting a change to running a job and delivering notifications happens smoothly, reliably, and also at the scale. Okay, so far we focused on one part of the system, how Semaphore runs jobs, but running jobs is not only it's not like the only part of the picture. Teams also needs to have a tools to configure the environment, to control the access, and integrate the workflows. And that's where the CI management comes into the play. While processing is all about running jobs efficiently, management is what gives user control over the environment. This is where developers and teams configure projects, manage secrets, and set up notifications, shaping the Semaphore to their needs. In these sections, we will start with an overview of how users interact with Semaphore through the UI and API. From there, we will dive into authentication and authorization, breaking down how access control works to keep the system secure. I will also show you how internal services communicates with HTTP handling external requests and gRPC used for internal communication, ensuring efficient and strict service contracts. Finally, we will go over how new services are introduced into the Semaphore, starting with a profile definition and ensuring a smooth and maintainable integration. Okay, so let's take a closer look at how Semaphore services interact behind the scene. So since user interact with Semaphore through the UI and API, all these communications happen over HTTP. However, internally, the requests follow a structured layered approach designed for security, maintainability, and scalability. We are using there the gRPC. Frontend and API services handling incoming requests, but they don't have access to the database. Instead, they communicate with dedicated backend services, which holds the business logic for managing projects, secrets, notifications, and other key system components. These backend services are responsible for enforcing rules, processing data, and ensuring each part of the system operates independently without creating a bottlenecks. This separation of concerns allows Semaphore to remain secure, modular, and flexible. It ensures that new features can be introduced without disrupting existing functionality, while maintaining a clear structure for how data flows through the system. And one of the most important aspects here in this CI/CD management flow is ensuring that the only right users have access to the right resources. Semaphore achieved this by separating authentication from authorization, allowing fine-tuned control over who can interact with different parts of the system. Before a request even reaches the frontend or API service, Authentication is handled by the out service, and this service verifies the user identity and inject the user ID headers to the request, ensuring that all downstream services can trust the authenticated user. To manage user sessions securely and seamlessly, we integrate with external identity providers. Semaphore relies on a keycloak, the robust and widely adopted open source identity and access management system. Once authenticated, the request moves forward, but access is not automatically granted. This is where authorizations comes in, enforced by the Airbag service. Frontend and API services call Airbag to check whatever the authenticated user has necessary permissions to perform the given action. After the verification, all internal communications is trusted, and meaning that services assume the request has already been authenticated and authorized. By keeping authentication centralized and authorization granular, Semaphore ensures security without compromising performance. And this layered approach allows for precise access control while maintaining system efficiency. Okay, so now that we've seen how services interact with Semaphore, within the Semaphore, let's look how we introduce new services while maintaining consistency and reliability. So as Semaphore continues to evolve, we constantly introduce new services to expand its capabilities. But adding a new service isn't just about writing the code, it's about ensuring that it fits seamlessly into the existing system without causing these disruptions. To maintain consistency, all internal communications happen via gRPC, which enforces a clear structure for how services interacts. And the first and the most important step when adding a new service is to define the service contract. And this is done by writing a protofile, which serves as a blueprint for how the services will communicate. It specifies the RPC methods, request and response structures, and expected data types, making sure that a clear agreement between services before any implementation begins. Once the protofile is in place, both sides of the communications needs to generate the necessary definition files, reinforcing a strict contract between them. From this point, the service is fully integrated and can be called just like any other existing component. By following this structured approach, we ensure that every service speaks the same language, minimizing the integration issues and allowing Semaphore to scale smoothly without breaking dependencies. So, Semaphore is a highly distributed system, carefully structured to separate CI/CD processing, where jobs are executed, from CI/CD management, where users configure and control the environment. In CI/CD processing, we saw how a Git push triggers a structured pipeline with hooks, pipeline orchestration, and job execution working together to ensure the builds run efficiently. On the management side, we explore how Semaphore allows users to configure environments with UI and API. A well-defined communication structure ensures that security and performance with external requests using HTTP and internal services communicates over gRPC. We also look at how authentication and authorization worked with Keycloak managing sessions, out handling identity verification, and Airbag enforcing permissions to ensure a secure and scalable access control system. Finally, we saw how new services are introduced into the Semaphore. By first defining the protocol contract, we ensure a reliable and structured integration process, keeping the system extensible and maintainable as it grows. Now that you have a better understanding of the Semaphore architectures and internals, I encourage you to get involved and contribute. Semaphore is an open source project, and your insights, feedback, and contribution can help us improve even further. Thank you for watching this.